So what can be wrong here?
Isn't it supposed to be M in the graph? I mean, that, sorry.
Let's check what will be if we would just shift our indexing in this way. So we will go that from higher lane it will be the previous one. So let's check if this one is correct. So it's the diagonal element will still be 0. And for 0, 1, quickly. Delta n plus 1. Okay. It will be still 0 here, but in the next element, it should. So this one will convert into delta. Okay, I will get back to equations later, but let's use common sense. So if we convert from state number 1, we should get state number 0. If we practice row by column, it will be matched if we have the all elements except this one equals 1. So if you start from 1 here, and if we get 0 at the end, we should obtain 1. So delta n plus 1, comma 1.
have it right the first time n minus 1 n, because then, because if you want the upper diagonal to be the one that's correct, so then you would want n minus 1 into n, because then n minus 1 equals 0, n would equal 1, n equals 1 equals 1.
So you think I want
N minus 1 in the first in the cat, and then bra should be n.
here?
Yeah, n minus 1.
Okay,
bra
let's
should be n.
try once again. Should I have?
No, just n.
Okay, let's check. Let's check. So if n 1 and here n minus 1 must be 0, which is equivalent to n equals 1. Good. And then here will be 1. Then the result will be square root of 1. Good? Okay. Thank you. So if, let me go here and make correction. N minus 1, n. Yes. Now, if this approach was correct, we should get square root of 2 for the element A1, 2, right? No. Correct. 0, 1, 0, 1, 2. So the element which stands down by in the second column, which has index 1, and in the third row, which has index 2. So we should obtain that this element A sub 1, 2 must be equal square root of 2. Let's check if we can get this result by practicing. By practicing the sandwich. So from 0, not 0, from 1 to 2, and put here the recently approved n minus 1. So n equals 2. And from these two bracket we get delta 1 comma n minus 1. We do, wait. Let's do continuously, not everything at once. Let's process this delta function first. So we keep this one at its place, and then we replace number n to number 2. And then we remove summation, square root of 2, 2 minus 1, and this one disappears, right? So 2 minus 1 will be 1, square root of 2. Here we get 1 and 1. This the factor can go out of bracket, and 1 and 1 by orthogonality will be 1. Okay, square root of 2. So let's, which other element will be non-zero? 2 and 3.
You don't put it 2, 3.
Hmm?
No, we don't put it 2.
You don't?
No.
Oh, okay. Good for you. But 2 and 3 should be square root of 3, according to this pattern. Whew. And if you will try any other elements, it should be 0. So we have only 2 non-zero elements. Square root of 1 here, square root of 2 there. Do you feel comfortable with these things? Give me a sign if you don't, because I do not feel super comfortable, as you see. For the first one, will you be able to do the same operation for a dagger? I did, but I'm checking for the future if we suddenly decide needs to do this thing for other algorithms. So generally it should work well with rigorous definition of operators. If there is no error, it should work. And there is also, one can always check if you're doing right things with common sense, by seeing how the operator converts different states. Okay, I'll make a little circle and personally check if some of this.
Just kidding. So far, there's only one. How's it with you?
Yeah, it's the schedule like that too.
You'll have space for
Yeah.
college.
I'm the only one in it so far.
Huh?
I'm the only one in it so far.
If you're curious about computational chemistry in the spring, on the books for registering, I have reserved like 2 hours for a lecture from 11 to 1, but I'm lying. It's just to prevent anyone else to come into the room, because I want to have like a free hour to upload things. Okay, so number 2 is you just analyze and tell that main diagonal is 0, upper subdiagonal are incrementing square roots, and all other elements is 0. Second subdiagonal is 0 as well, right? here. This belongs to second subdiagonal. Why this question? Because later there will be a couple of other operators when second subdiagonal will be non-zero. How do we do this one? What do we need to practice this question? Which materials from internet we may want to get in front of us, or which parts of lecture material we may need? So what is required in this question, and what do we need to complete it? So it tells to express some operators in terms of creation and annihilation operators, right? Is it sufficient to have only this definition? Or we need a little connection, little bridge to real life? So how these operators were originally defined? When we started using annihilation operator as a shortcut to find ground state, what was the hypothesis? How did we represent it?
If you apply it to the ground state, it would equal 0.
Yes, it is result. But how did we formulate it? Where did we take the functional form of the operator? We decided that we do not have too many operators, and we may try to take something that we already know and combine it. No? 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 I'm with you. I do not mind that you do not recall things quickly, because sometimes I do that. No? No? What else? Huh? They are Hermitian. But, like, is there any other definition? Like, can we write that like A dagger equals to something different? If some of you is looking in Wikipedia for this ladder operators, what do you see there?
Yeah, I got it.
Like definition. But you know, some people do not have enough strength in memory to recall this stuff. Can you summarize it by human words? What is there? What is later after this scaring coefficients?
There's R and I and E.
Huh?
Position.
Yes, position and momentum, right?
Yeah.
So it is a superposition of position and momentum. Okay? Do you recall something like this?
I see it in my notes right now.
So
Yeah.
it should be position and momentum. And there are, so what you are invited to recall is that there is a superposition of position and momentum. The rest of coefficients is very understandable if you do not recall it from the top of the head. And what is the main principle for this scary coefficients here and there?
You multiply all the annihilation equation.
Absolutely correct. What else? What is that? What is the dimensionality of position? Okay. What is the dimensionality of momentum? Okay, kilogram times meter per second or whatever. What is the dimensionality of Croatian operator?
Same as oh, is it dimensionless?
Yes. So these factors are designed in such way so that this superposition will be dimensionless. So it is something I can recall. Therefore, I can ask you to recall it as well. So factors for dimensionless. Factors to make it dimensionless. So if someone told Hermitian, right? Which means if you have expression for one of them, then another one will be just swap sign in front of imaginary unit. So the question in the assignment asks to express position and momentum in terms of creation and annihilation operators. What if we take these two equations and add them together? So on the left we'll have A dagger plus A. On the right we'll have the factor is the same. And here we'll have 2 m omega r, because these terms, coefficients in front of position are the same, so you just multiply by 2. And what will be the coefficient in front of momentum?
0.
Yes, plus 0. What should we do to solve for R, for position? Just practice some basic algebra, right? So maybe remove this 2, square root of 2, square root of omega, and here. So, and remove h bar, and here square root of h bar, right? And then we multiply both left and right sides on this factor. So h bar 2 omega square root a dagger plus a equals r. Again, do not trust me, please check for errors. I'm a champion in making errors. So this, if it is correct, if no one finds errors, and if there are no errors, it will be answering the first question. The position as a function of creation and annihilation. The next thing is to express momentum as function of creation and annihilation. So I'm practicing this calligraphy once again. A dagger A, 2 H bar, 2 omega H bar, M omega R, minus IR IP, M omega R plus IP. So what will happen if I subtract these two equations from each other?
So A minus A big, you get 2 IP instead of 2 and
Right. Minus 2 IP. So here will be 0 in place of position, and here we just keep the same square root of 2 and omega H bar. A dagger minus A. So one needs to solve for P, right? So A dagger minus A divided by minus 2I multiply by square root of 2 and omega H bar equals P. And then we can cancel 2 here and put square root of 2 in the denominator. And if we do not like minus here, we can swap and subtract A minus A dagger divided by 2I. Just divide by I. Square root of M omega H bar by 2. Any errors? Do not give me a chance to make them. I like to do errors. No? Okay, so then we are done. Well, it is important to check for errors or their absence because the next questions are built upon those intermediate answers. So the next question is total energy, kinetic energy, and potential energy. So for total energy, we can go with our Hamiltonian in terms of ladder operators, where one would get just A dagger A times H bar omega. But it could be right, it is right. But if we didn't knew this shortcut trick, we may try to express kinetic and potential energy in terms of these, how to say, transformations, definitions. So for kinetic energy, E sub K, we get P squared over 2M, right? So we would plug in 1 over 2m, plug in this definition. So m omega h bar divided by 2. So we remove square root because we are taking square. And then we have here a minus a dagger divided by I squared. Kinetic energy. Mass cancels. So 1 over 4 omega h bar omega. I squared will be minus 1. And here we have a square plus a dagger square plus minus a dagger minus a dagger a. Well, one can try to simplify it further, but this one is not too bad. So, if we look on the next questions, next assignments, the squares of the creation and annihilation operators can be responsible for providing second subdiagonal. Another interesting observation here. Is it better? Another interesting observation that energy, kinetic energy, is proportional to h bar omega, right? So we didn't do any tricks. We literally played with definitions, plugged in, and here you see the kinetic portion of energy is some combination of these ladder operators multiplied by Planck constant and frequency. So if we know the frequency of oscillator, it's sufficient to know its energy. We already knew it from previous considerations with kinetic energy. Now let's practice the potential energy. So potential energy how do we formulate it? It's position squared with some coefficients, right? Right? Good. So we just plug in this answer for position into this definition of potential energy. So h bar to omega. Now we do not have square root because we are taking square, and here we have a dagger square plus a square plus a dagger a plus a dagger. So today I'm not super brave, and therefore I'm not practicing commutation. But I know that commutation is important, and therefore I do not swap the orders. I just, like if you do algebra with regular variables, you would immediately write 2a dagger a, right? But here, no. It's dangerous, because swapping will do something. And if you are not sure what to do, just keep it in this order. So what can be cancelled? Mass can be cancelled. Second power of frequency can be cancelled. And then you have 1/4 h bar omega a dagger square plus a dagger plus a dagger a plus a dagger. So we have potential. Now, let's make a little experiment and express total energy as a summation, of kinetic and potential energy. So for kinetic energy, we've got negative h bar omega by 4. Then we've got a dagger square, e square, and then there were minuses, right? Minus a dagger a minus a dagger. So this was term for kinetic. For potential, we have plus h bar omega over 4. A dagger square plus a dagger plus a dagger a plus a dagger. What do you observe? What do we observe? They look very similar, very symmetric. Some terms are going to cancel. So this one will cancel, this one will cancel, right? So second orders of accretion and annihilation will cancel. And because of here there is minus and here there is minus, the total will be plus. So slowly but surely, h bar omega by 4 plus 2 a dagger a from this term plus 2 a dagger. Right? H bar omega divided by 2 a dagger a plus a dagger. So this is sufficient for a grade, but if you feel brave, one can simplify it a little further. There will be one of the subsequent questions about co-mutation. Which means a dagger equals a dagger a plus 1. I'm just impatient because then it will feel so much more comfortable. So if we plug in this expression into here, then your total energy will be h bar omega over 2 a dagger a plus a dagger a plus 1. Right? No one put me on error. Probably I feel comfortable. Here it looks correct. The simpler the equation, the more correct it is. So these two are the same, right? So we can remove one of them and put factor 2. And then factor 2 here and there will cancel. So this 2 and this But here we will have 1/2. So the answer for total energy will be h bar omega E dagger A plus 1/2. So dimension of energy is dimension of frequency multiplied by Planck constant, right? Because creation and annihilation operators are both dimensionless, right? But instead of just product of these two operators, there is a constant, which will be present even for ground state if when this combination of creation and annihilation will give zero matrix element. And this 1/2, this constant, originates from commutation of these operators for harmonic oscillator. Let me walk and see how comfortable you are with this. Otherwise I will be exhausted too quick. I don't know how to assign words, but I feel it's okay. There will be some other things. Yeah, I will not do the.
What is this asking?
Repeat steps.
This 1, 2, right here?
Yes. Huh? Yeah.
Oh, and then you use the position from here and yeah, that's gonna be yeah.
Yeah, that makes sense. When you say step 1 and 2. Oh, okay.
Diagonal, subdiagonal position.
Oh, I have it. I need yeah.
Do you feel comfortable with commuting annihilation and creation operators with Hamiltonian? Do you need any instructions or you're fine?
Are we using the handle for that?
Yeah? Would you like to try? Let's try. Just I need a breeze and I will help.
Do you want me to come up?
Yes, yes.
Okay.
So
Yeah, I know. I realized that when I put it on. I was like, it's comfortable. It's a high school teacher. Hey, I actually had to pay for this. I'm still wearing it.
okay, please.
That's probably really small. A little bit.
Okay, so now Alex is practicing definition. Keep going, keep going. Well, one can probably put the factor constants out of brackets, right? So far, so good. And now one can open this two little brackets. Two round brackets, right?
Can I put square?
Yeah, you can, but it is safer to write just continue as it will in matrices. A dagger A. Okay. Yes. A dagger A minus so can you cancel anything? So this first power of A can be cancelled, right? Because it is with plus and minus. So what do we get after cancellation? Okay, so there is a rule of thumb suggestion to try to arrange operators in the order that daggers go first, no daggers go second. So the first term has a dagger and then two A's. It's good. With dagger is higher rank. It goes first. But the second term has a mix of with and without dagger. What should we do in order to swap the order? Can we put this A dagger earlier than A? Can we swap the order of these two operators?
Can we use this?
Yes, exactly. Everyone see what he's doing? So the A dagger is replaced by definition of commutation of these two operators by A dagger A plus 1. And then Alex opens brackets, and what is the result?
You just multiply to get A dagger AA plus A.
So the result of commutation between Hamiltonian and annihilation operator is
H bar omega.
factor times annihilation operator itself. Okay, interesting. Yeah. Okay. Thank you, Alex. That's an achievement. Good.
Huh?
Second line. There you go. That's 2 bar.
It's 2 times the bar.
Michael, can you repeat the same heroic feat for A dagger?
Del plus.
Oh, it's oh.
Yeah. Yes. Excellent. Negative. Perfect.
Still.
Yeah. Thank you for taking care of the records. Yes, the negative comes from this. Very good. Good eye. So, do you need to have this?
Oh,
Do you need these records to be on the board for a longer time, or you got it? Then erase.
can I just?
Okay.
And then,
Take another color because otherwise
Oh,
you
yeah,
can
yeah.
get a big mess.
let's-
What about AO2? Yes. So it will be A dagger A dagger A, right? Okay.
Hang on, no,
No?
No? Why no?
because the A, J, and the brackets, the A dagger would have to go before the first term. Because it's A dagger comma H, not H comma A dagger.
Right here?
No, that way back at the beginning. You have to flip those two around because it's A dagger H instead of H.
No. H bar omega are not operators.
No, but the A dagger A plus 1/2 A dagger should be A dagger times the parentheses. Because it's A dagger times A bar.
Wait. Telling about first term or second term?
Both terms, so don't. Because it's not, it isn't just this, it's this. So you have to switch these two terms. So you can't just start.
Wait.
Because you're asking for this, aren't you?
Oh, but this is so simple. You can do this one and then put minus in front.
Yeah,
You know, if you swap the order, like. So if you swap order, you just put minus sign.
Okay.
But thank you for caring and checking. But keep going with your original writing.
let's
Okay.
do this because
Okay.
oh, delete. Okay.
Okay. So where do you stop? On this line. Okay.
I think it was done with that.
So the cancellation of
These
of,
two.
of these two is the same. You can cross them
Yeah.
through so that we do not feel confused. Yeah.
Okay.
Now, how do you place? So if we have a daggers first, no daggers second, it is normal ordering. It's good. If we have mix, then it is something strange. So which of them have? Okay, yeah. This one doesn't have normal
Okay,
ordering.
I'm gonna put over.
Or you can erase masterpiece of Alex because we all.
We all got it?
Yeah.
Okay.
So just erase stuff here. Probably things will be different.
Yeah.
That one is better visible. Dagger. So A dagger A plus A dagger minus A dagger A. So the first and last terms cancel, right?
Yep. So we made negative because of this.
Excellent. Oh, it is because
Because of that. Yeah.
so commutation between Hamiltonian and creation operator is constant times creation operator, right? Good, good. Perfect. And you will do extra credit on your own, right? If you like to. So everyone is ready to go to the MATLAB part of the homework. So what is the goal and scientific meaning of this MATLAB part of the homework? What are we going to get? How does it will connect to other parts of the course? So remember when we did the free space, we originally hypothesized before solving any equations what will happen to Gaussian distribution. It will move forward with constant velocity, and the width of the distribution will expand, as we later saw, quadratically, right? So, although quantum theory gives complicated multidimensional distributions, for some situations one can summarize outcome in a simple energetic expressions, right? For free space, Gaussian wave packet moves and expands. What does Gaussian wave packet makes in the harmonic potential? What does classical oscillator makes? What does mass on a spring perform? Yes, oscillations forced and back, right? So for quantum oscillator, the Gaussian wave packet will also shift its center to the left and right harmonica, right? But the question is whether the quantum nature of these equations will make any specific changes to the shape of Gaussian profile. Will it expand, shrink, or does something else? And this was one of the questions in the previous homework, last question. Anyone wants to declare? It's one opinion. Were there other opinions? I have records of your homeworks, and there were several correct answers. Okay, even if you do not recall the answer, we do have a good formulation of question. How the quantum theory for interatomic distance will affect the distribution, shape of the distribution. We kind of hypothesize and we can prove that center of the wave packet will oscillate. And we want to get rid of this effect. We want to focus only on the width. Therefore, if we set up initial position right at the equilibrium, and we set up no initial velocity, no initial momentum, it will just sit above the equilibrium. So we want to see only effect on the width, right? So how do we do it? Let me invite you to open the code, maybe the one with comments. And go to the part where the potential is defined. So whatever the last expression will be the only one that will work. So I'm going to line 59, and just to make life easier, uncheck the uncomment this line. So from now on, the potential will be quadratic with center at 40 atomic units from origin, with this m omega square over 2, this rigidity constant 5 divided by 1000 in atomic units. Then I can go into, upon this change, I can go into the very beginning of the code and make sure that the momentum is 0 and position is equivalent to equilibrium. Whatever was the center of the potential will be the same for our initial position. Okay, then I'm saving it and erase all. Okay, and just run the code. I will not run it because I want you to have the feeling of discovery. So please try.
Running so safe. It's a main observation. So instead of expanding, you just expand and shrink. Well, this is what have you seen? No. Have you seen that?
It's like on.
What is it? What's numbers still to the same position? Just yes. It's like a person practicing weight control. Losing weight, gaining weight.
Yeah.
Have you seen it? Can you set the initial position to say 40%? Very good. Instead of 30, and for the people, it's 0. Save. precise. So it's weight control. So it's getting thinner and thicker, and you see that two different methods, depending on definition on momentum, do not they diverge, but not much. So it's kind of trustable results. So how do we process? How do we interpret? What do we plot upon completion of this experiment, numerical experiment? We will look for what is required in the homework assignment, but likely one would need the variance, the uncertainty, the width of the wave packet. So let's look through the code if you do not remember the variable. So I invite you to look at the line 209 and 215. So you see it is average position minus position squared, and then taken the expectation value. So it is uncertainty of position by method 3, and then this instantaneous value is accumulated into the variable variance 3. So likely we are interested to plot this variance 3. When there is a multi-plot figure, one of the panels will show it, but if you have a couple of minutes, it's better to have full control and either redraw it or find a line which plots it. So variance 3. If we are looking onto lines 218 and 220, it will be the same thing, but depending on the second method. So variance and variances. So what we may want to do right away is to plot time variances, comma, time variances 3. See what happens. Okay. Cool. So this is width of the wave packet. The number 8, there is initial value, which you also define at the first lines of the code. And what you see that width decrease, and then starts growing back. And these two lines are results of different methods. So they predict basically the same behavior with relatively small error. And we will look in what is required very soon, but you can see that width oscillates, right? Instead of growing. One of the if you look on this multi-panel window, sigma sub x, you see here the quadratic growth which would correspond to free space, and here is oscillation observed in harmonic potential for the width. Now let's check what is required. Consider different initial values for what? For sigma x. Which means we may rerun stuff by changing the x var variable at the very beginning. Right now it is equals 8. Later on we can try different values. So what is the dimension of sigma x? Probably you'll be able to answer yourself, right? If dimensionality of power of the exponential in the Gaussian is dimensionless, and the denominator is position squared, then the denominator should be length squared, right? Find width of for the ground state of this harmonic oscillator. Okay, I apologize, it is a trap. It is a trap in a sense that this part of homework is announced as purely MATLAB running, but maybe to answer this question 2, one needs to write a couple of equations. Please give me signs if you do not understand what is asked, what is required in this question number 2. Means you do not understand. Now give signs if you understand what is required in number 2. Okay, give signs if you are 50% sure. Okay. So the thing to do is to recall. I know it is the adverse thing that you hate at most. To recall, to remember the expression for ground state wave function. Find width for ground state of this harmonic oscillator. So I'll start doing it because it will be much easier to get over when it is more practical. So I think Alex and Michael will not object if I erase their glorious achievement here. It's already on the recordings. This one is also. So yes,
The sigma x the wave function, or is that the variance?
variance. So find variance for ground state of this harmonic oscillator. Sigma x 0 for ground state. So on one hand, we need expression for wave function of ground state. On the other hand, we do have Hamiltonian that we assumed in by solving this stuff. So we agreed that it will be 0, 0, 5 times x minus x naught squared, right? Not Hamiltonian, only potential energy. Yes, good. So we need to recall this equation and and connect these two things. Recalling is hard. I will start with easier thing. So if we set up this constant, it means that m omega squared over 2 is equals 0.005. Somewhere in the formulation of the problem, it tells that we know typically it is protons or atoms of carbon or something. Typical oscillations is oscillations of nuclei interatomic distances in molecules, right? But here, just for simplicity, we will assume that it is a problem for an electron, because otherwise it will be too much conversion of units. So if it is an electron, then mass equals 1. And then life is easier. So we plug in mass equals 1, then it will be omega squared over 2 equals 0.05 in atomic units. So multiply by 2, omega squared equals 0.01, right? And omega frequency will be 0.1 in atomic units. So we know the frequency, right? So it's kind of arbitrary. We just took good number, simple number to play with, but later on in projects, or maybe in some other problems, we can focus a little bit more on details. What is the mass? What is the frequency for a specific system? If it will be sufficient. Now it is sufficient. So if you know this rigidity coefficient and we know the mass, we can extract frequency. Now let's practice our memories. I'm with you. It's so hard for me as well. So I remember there is a square root of square root, or 1/4. There is an exponential minus something times r or whatever, x squared. I remember that here there was a fraction, and there was a h bar, and it was number 2. Anything else we can remember? Right? Good. Thank you. Thank you. So, the question is to make connection between left and right side. To express what will be ground state variance for these parameters of the oscillator. So let's screw scroll through the code and see how does this code uses the variable. Probably there is a very thin third code variance. Or xvar. Okay, we have xvar for initial variance, and there is a psi naught after the potentials. Okay, here. So this is a part for the plane wave, this is for normalization, and here is elongation squared divided by 4 xvar. So for initial condition we use e to the minus x squared divided by 4 x, it is variable x var, and it is the same that we call sigma. It's not here. It's not. So the question is, and at the beginning of the code we set up x var equals 8 atomic units. But what would be natural width? What will be the width of the wave packet if we artificially set up our initial condition to be ground state of our oscillator? When we ran the code 10 minutes ago, we just did arbitrarily width just centered on the zero. But due to normalization, ground state of oscillator has certain width. It is likely that we took a little bit bigger. What would be the optimal width? So I'm going to make a connection of this box and this box. So from here to h bar divided by m omega, it's inversion of this one, is equal for x var, or 4 sigma. So I can solve it for this sigma naught, just dividing everything by 4. To here. So sigma x naught equals h bar over 2 m omega. Right? So h in atomic units, h bar equals 1, mass equals 1, frequency equals 0.1. So 1 divided by 2 is 0.5, and 0.5 divided by 0.1 will be how much? Same as multiply by 10, right? Divide by 1/10 is same as multiply by 10, right? Okay. So 0.5 multiplied by 10 will be right. So by comparing our chosen shape of potential and equation for ground state wave function, we can express the natural width of the harmonic oscillator in terms of these numerical values. So right now we do have some reference point. So we are going to play and run the code a couple of times again with different value of initial variance. But right now we are not blind. We have reference point. And maybe it will make sense to check the initial variance equals to this point, a little bit higher and a little bit lower. And then observe what will be the consequences. Make sense? So, suppose I take 2 instead of 8. So I will try 8, 5, and 2. Higher, lower, and right in the center. Save and run. So please do the same, and I will circle around the audience. So if I want to compare the results, I was keeping the older image aside. Now I can type hold on and repeat the same command. So this line that starts with 8 was when your initial x var was 8, so it shrinks. It gets thinner and gets bigger. When you start for 2, it expands and then shrinks again, right? So let's put initial variance 5 according to our calculations and see what happens. Maybe keep aside this figure so there will be third set of lines. So please run, and I will circle around to check which discoveries you are making. So, do you run? So what do you see? No, if instead of 2, you set x var to 5. Same value as with analytical table. Doesn't change. There's variance, there's shape of the wave, but it changes. So it's discovered.
Yes.
You see that you see nothing. The wave function, wave packet stays the same. That's a great discovery. It's not very spectacular, but it is. Were you able to see that there are changes, but they are like vanishing? This one.
Oh, yeah.
If you set up variance equals 5. Okay. Okay, so in a minute we will look what is listed as request, but how do you interpret this observation that shape of wave packet doesn't change? It doesn't move anywhere and it doesn't change the shape. We all are on a threshold of a great discovery. It's really not spectacular, but it is a big connection to the whole class and whole quantum theory. So let's scroll back. In which cases we explore the dynamics for each initial states? Remember the first time we tried some dynamics for particle in the box with superposition of ground and first excited. When you saw it bump for some time. So it was not eigenstate, not stationary state, right? It was superposition of several eigenstates. So the dynamics is observed if it is superpositional state. But if it is one of the eigenstates, it is expected that there will be no dynamics. Right? It will be boring. Eigenstates are also often called stationary states. Nothing happens. Now we flip the logic in the other direction. If you see that the state doesn't change with time, what does it mean? Yes. So right now we created system in the eigenstate. Therefore we see no dynamics. Right? So the following 10 seconds or 1 minute will never be applied to this class. But I've observed several styles of teaching of quantum theory as a student, as a company instructor, and I saw several labs where one is offering to the class to design arbitrary wave function, plug it into Hamiltonian, and see what happens. And if the nothing bad happens if it will be eigenstate. If something bad happens, it will be not eigenstate. This approach, we are not going to practice because it's senseless, but it is kind of a test. If you design an arbitrary function and you see that it doesn't change in time, it's one of the ways to find eigenstates. Right? So you can creatively design some shape, make it in mathematical equation, plug it into the code and see. If it moves, not eigenstate. If it doesn't move, eigenstate. Not very efficient, but if you write, suppose we do not know the theory, we do not know the answer, we can make a robot, a little code that will design shape of a wave function by random numbers, throwing dice. Right? You know random numbers. So random number at one point and another point, and then throwing it into the code. And by repeating this procedure again and again, one can find such states that change at least. And tell, oh, okay, right, it isn't like this. So another observation. Let me bring up the thing that we put aside. Hold on and repeat the same command. So you do see when we put initial variance smaller than the value that we derived analytically, it grows and shrinks. If we put it larger, it shrinks and grows. If you put it in the right place, it doesn't change. So, how else we can interpret it? When the width is big, it is uncertain. When it is narrow, it is more certain. So in harmonic oscillator, the uncertainty of position may oscillate, right? Less certain, more certain. Wider distribution, narrower distribution. Okay, let's look again on what is asked. This stuff. Plug in this value into modified code. We did. Report by words how sigma x depends on time for this initial value. You'll be able to write it. It depends trivially, showing no dependence, constant. If you plug in the this width, but when you will be preparing your homeworks, probably you may want to give this little derivation where it comes from. Report by words how width depends on time for larger and smaller initial values. It is what we did, right? Okay, and the rest are extra credit that you can get through yourself if you like to. Whew. We are done with main part, and there is no time for the potentials. Let me just show part of the code that we will start from on next Wednesday. And if some of you are so dedicated to design potential, you may play with it. So. So if next time we will practice this chunk of the code from line 32 to 43, and at the end we will write v equals vv and then comment out everything after. Then it will give a model of a chain of atoms, electron moving through chain of atoms. Okay, done?